Science is not just the pursuit of knowledge, it is the foundation of a nation's progress. Good morning, distinguished guests, respected scientists, faculty members, staff, and dear students. It gives me immense pleasure to welcome you all to the celebration of National Science Day at CSIR 4PI. Every year on February 28th, India celebrates National Science Day to commemorate the discovery of the Raman effect by the great Indian physicist Sir C.V. Raman, a discovery that earned him the Nobel Prize in Physics in 1930. This year's theme, Women in Science Catalyzing Viksit Bharat, beautifully reminds us that inclusive excellence is the foundation of a developed India. To mark the auspicious beginning of today's program, I invite our dignitaries to kindly come forward for the ceremonial lighting of the lamp. I request our director and dignitaries to kindly take your seats on the dais. I now request Dr. Imtiaz Ahmed Parvez, Chief Scientist and Head IDRD and TMD, to deliver the welcome address.
Good morning all. Dr. G.K. Patra, Director CSIR 4PI, Professor B.S. Dayasagar, Head Indian Statistical Institute, Bangalore, and the chief guest of today's function, Professor Gaur, Dr. Bogle, Dr. Mutkavi, Dr. Dutt, and all the distinguished members of the dais, colleagues and friends. Good morning and a very warm welcome on behalf of myself and on behalf of CSIR 4th Paradigm Institute. It's great pleasure to welcome you all to the celebration of National Science Day. As Anna mentioned, we all know that this day observes the discovery of the Raman effect by the eminent Indian physicist Sir C.V. Raman, a discovery that brought global recognition to Indian science and continues to inspire generations of researchers. And the theme for this year, National Science Day, Women in Science, Catalyzing Viksit Bharat, that highlights the crucial role of women scientists and innovators in shaping India's scientific and technological future. It reminds us that inclusive participation in science is essential for building a knowledge-driven and developed nation. At CSIR Fourth Paradigm Institute, where computational science, data-driven discovery, and interdisciplinary research are central to our mission, we recognize our innovation flourishes when diverse minds collaborate and contribute. Today's program provides us an opportunity to celebrate our scientific achievements, encourage young minds, and reaffirm our commitment to advancing science for the benefit of society. To mark this occasion, we are very fortunate that today we have with us very distinguished scientist, Professor B.S. Dayasagar, who is the head of Indian Statistical Institute, Bangalore, and he has agreed kindly to grace the occasion as a chief guest. It is an honor for me to introduce our chief guest, but before I start, I request our director, Dr. G.K. Patra, to formally welcome our chief guest with a plant. Thank you, Dr. Patra. Now, introducing our chief guest in 5 minutes or less than 5 minutes is a challenge. His profile is really very strong. I'm trying to summarize that we can fit into the time, but anyone who is interested may just go to the website and read his profile. Professor B.S. Dayasagar, who currently serves as the head of the Indian Statistical Institute and professor in the Systems Science and Informatics Unit. He completed his BSc, MSc Tech and PhD from Andhra University, laying the foundation for his distinguished career in mathematical geoscience and geospatial analytics. He is an internationally acclaimed scientist whose research spans mathematical geosciences, fractal geometry, mathematical morphology, geospatial data science, and remote sensing. Through his pioneering work, he has contributed significantly to advancing mathematical and computational approaches for understanding complex Earth systems and spatial phenomena. Over the course of his distinguished career, Professor Dayasagar has published more than 100 research papers, including over 80 articles in leading international peer-reviewed journals, and has edited around 11 scholarly books and special journal volumes. His work has had a profound impact on the global scientific community, practically in the field of mathematical geosciences. His outstanding contributions to science have been recognized with numerous prestigious awards and honors. If I list them, it will be a very long list. I just name few. That includes Krishnan Gold Medal. He is a member of the New York Academy of Sciences, Fellow of the Royal Geographical Society, and several other national and international recognitions. He is also an elected fellow of the leading scientific academies such as Indian Academy of Sciences and the Indian National Science Academy, reflecting the high regard in which his scientific contributions are held. In addition to his research achievements, Professor Dayasagar has played an important role in nurturing scientific collaborations and community building. He has served on editorial boards of leading international journals and has been actively involved in organizing several international conferences and scientific activities. On the occasion of National Science Day, which celebrates the discovery of the Raman effect, it is particularly fitting for us to have with us a scientist whose work exemplifies excellence in scientific inquiry and interdisciplinary research. Dear friends and colleagues, please join me with a big round of applause to warmly welcome Rajvi. Thank you once again and very warm welcome to this National Science Day. Jai Hind.
Thank you, sir, for your warm welcome. As we celebrate the invaluable contributions of women in science, and in respect to this year's theme, Women in Science Catalyzing Viksit Bharat, it is my privilege to invite Dr. Usha K. Hasyagar, scientist at CSIR 4PI, to deliver a talk.
Good morning all. Today I'll be talking about two women atmospheric scientists who were the catalyst in the Viksit Bharat vision. That is Anna Mani and Professor Sulochana Gadgil. First I'll be talking about Miss Anna Mani, the woman who measured the sky. So she was born in 1918 in Kerala. That is the time when the society, and did not encourage the education of the girls, where the literacy was less than 1%. So she grew up in a traditional household where the girls were expected to prepare for marriage but not science. But she was into books, like she had read all the library books, and she wanted Encyclopedia Britannica instead of the diamond gift from the parents. So then she completed the BSc in physics in the Presidency College in Madras, and then eventually joined Indian Institute of Science under the Nobel laureate Sir C.V. Raman. She was one of the prominent students of C.V. Raman, and she studied extensively the diamonds. She continuously day and night, because that was the peak topic in that lab that time. And she produced 5 research papers. Most of them were single author paper, but she could not get a simple PhD degree because she did not hold a MSc. So what next? So what she tried is, she got a government scholarship for the research internship in England. She was so focused on physics, she really wanted to do in physics, but she could not get a physics internship there. So then she transitioned into the meteorological instrumentation. Not so glamorous, not so famous, but it was a very essential at that time. And with the skill developed there, she then came back to India and she joined Indian Meteorological Department in Pune. This was just after India became independent, and this was the time when India heavily dependent on outside imported instruments. And her mentor, Sir Venkateshwaran, wanted India to manufacture their own instruments. So she was very pivotal in that, and she guided the design, calibration, standardization of over 100 weather instruments, rain gauge, hydrometers, barometer, etc., which was designed within India, in-house. Okay. So further, she wanted to have more focus on the solar energy and wind energy, renewable energy over in India. So she wanted to harness the solar energy, and she faced the problem. There was not many historical records of sunlight distribution over the Indian region. So she went towards that, but then she became more focused on the studying on ozone layer, which is as we all know, it's a thin atmospheric shield which protects life from the harmful UV radiation. So she designed an instrument called ozone sonde. It was already there. It was a European design was there, but it had a lot of errors in that. So the one she designed was much more accurate, and she attached these to the large balloons, and it had to let it go, and then it will travel up to 30 kilometers at height, and it would measure across the atmosphere as shown there. So this made the first precise seasonal measurements of ozone content in the tropical region. So this was way before when we knew the life-saving importance of ozone layer. It was like way 20 years before the global scientific community could know that. And later, she found a company manufacturing the wind and solar instruments, believing that India's renewable and future dependent on the precise measurements. So she was something like she knew that Atmanirbhar science is the foundation of the Viksit Bharat back then itself. Then now, Anna Mani measured the sky, but the monsoon, which is the lifeline of India, is not just something we can just measure. It is something we need to understand. So understanding its variability, its active break cycle, became the life work of Professor Sulochana Gadgil. So she is one of another atmospheric scientist who was the pioneer in monsoon science. She was born in Pune, and unlike Anna Mani, who had a background in physics, she started with mathematics. Her bachelor's was in mathematics. She earned the PhD in applied mathematics from Harvard University, and then she worked as a postdoctoral fellow in MIT, USA. She was working with Jules Charney, who is called the father of the atmospheric science. And then she came back to India and she joined the IITM. And further, then later she joined IISc, where she stayed till her retirement. And this period where she during her career time, it was the time when she was the forefront of the revolution that occurred in the monsoon science. This revolution was largely driven by the satellite advance and the computational advancement. So I'll be talking about some of the key work what she has done. So one major work what she did was she before the understanding that was that monsoon is just a big land sea breeze. So based on the thermal contrast between the ocean and the land. So but when she came to IISc, she started excessively studying about the satellite data, and she studied daily evolution of the the cloud bands, first of all, the satellite map of cloud bands. And she studied the daily evolution and formulated the theory that monsoon is nothing but the northward movement of the intertropical convergence zone. So it is not just a local phenomena, it's rather a global weather system that is not governed by the factors like local contrast, surface temperature, but rather the movement of the sun. Later, she also showed that before it was just the understanding that monsoon had strong correlation with the El Nino Southern Oscillation, ENSO, which is the sea surface temperature variability of the Pacific Ocean. So here she formulated a composite index combining the ENSO as well as the equatorial Indian Ocean circulation, and which is Equino, and provided the strongest, which provides the strongest association with the ISMR, proving that improving the monsoon prediction significantly. And further, her contribution to the Indian monsoon and the agriculture relation, she showed that 20% in decrease in the summer monsoon rainfall would reduce the crop production 20%, but similar increase did not increase the crop production, which revealed that farmers' limited capacity to benefit from the excess rainfall. Now her contribution as a scientific leadership and the institutional impact, she was a member of the World Climate Research Program, and she spearheaded the creation of the Indian Climate Research Program ICRP in 1996. This under ICRP, India led its first coordinated nationally funded field campaign over the Arabian Sea and Bay of Bengal. Before it was largely funded by the outside sources. So this created a large critical data of monsoon humidity, sea surface temperature, salinity, etc., which strengthened the Indians' independent climate research capacity. She advocated for the mission mode approach for the monsoon research, which led to the launch of the National Monsoon Mission at 2012. This mission has fostered collaboration between the Indian and the international scientists and advanced the understanding of the atmosphere and ocean interaction. And it has significantly improved the accuracy of the extended range monsoon rainfall forecast. She has actively promoted the monsoon science education. She has a lot of articles in the Resonance, and she delivered a lot of NPTEL lectures on the monsoon and its variability. She was elected as the fellow of Inside Indian Academy of Sciences, and she received the Lifetime Achievement Award by MOES in 2016 and the Gilbert Walker Gold Medal in 2017. So, in a developed India, a developed India is not built on only infrastructure. It is built with the instrument, ideas, and the courage to ask the difficult questions. Women like Annamani and Sulochana Gadgil gave India all three. Thank you.
Thank you, ma'am, for your insightful talk and a glimpse into the contribution of women in science. Now we move on to the highlight of today's program, the National Science Day Lecture. We are deeply honored to have with us our chief guest, Dr. B.S. Dayasagar, Head Indian Statistical Institute, Bangalore Center. Sir, I request you to grace us with your talk.
This is previous and present hold is like this pointer set. Present hold next set. This is previous.
On this side.
It's okay.
It's okay. Good morning. It's a great honor to stand in front of Professor Gaur, Dr. Bogle, Dr. Datta, and Dr. Mutkavi, and several other colleagues and people with lot of experience. It's a great privilege to be here. And then when Gopal has asked me that I should give a popular talk, I was thinking which is the appropriate topic. The topic I spent mostly on mathematical morphology and fractal geometry, but not independently, but showing some connections between morphology and fractal geometry. I know all three of them whom I mentioned here. Georges Mathran was treated as a father of geostatistics and also co-founder of mathematical morphology. And John Serra is the founder of mathematical morphology. And Mandelbrot is, we all know, he is considered father of fractal geometry. And one initial connection between the two topics of mathematical morphology and fractal geometry, the founders are the students of the same Professor Paul Levy, and who was considered as father of probabilities. And Paul Levy has produced 4 great minds, and 2 of them are here. One is Georges Mathran and another one is Professor Mandelbrot. And then to just give you a very brief gist about morphology. Morphology works on shapes. And mathematical morphology is, many people used to ask, and we come across numerous kinds of shapes across geology, geoscience, geomorphology, biology, and across all disciplines. And is there a mathematics which can really be very useful to characterize and quantify those shapes and functions? And I can confidently say that mathematical morphology is one of the powerful mathematical fields which can really explain, but unfortunately it is not so popular beyond Europe. And I have asked the same question to John Serra. what is the reason? Wavelets were so popular across the globe, and why not mathematical morphology? He has put the blame on Georges Mathron. He never liked to travel beyond France. But I said, Professor Serra, you have traveled, but I never liked America to settle there, and then so I came back, and this was the reason he mentioned. But truly, and I thoroughly enjoy mathematical morphology because it has complete mathematical basis, and then it has been so successful in not only in geosciences and mining engineering, it is very successful in computer science, digital image processing, image analysis, and computer vision, and you name the field and it has a role to play. And of late, I have used it in some kind of spatial econometric kind of studies, because it gives a wonderful distances, not those distances won't follow any triangle inequality properties, but asymmetric distances, they are really useful when we talk about the force of interactions between the trades of the two countries or two states or two districts. And as I mentioned, the true definition of mathematical morphology is it's a nonlinear set theoretic theory and technique, and which will be very useful for quantifying the geometric structures and functions purely based on set theory, lattice theory, topology, and random functions. And the other one is the Mandelbrot's fractal geometry. It talks about the symmetry. It is not the symmetry between left to right and top to bottom. It is the symmetry across the magnifications, across the scales. And to be precise, and morphology talks about shapes, and fractal geometry talks about scales. And we found out, and it is not just the scale invariance property that we would like to have, and we want to see some measures which are scale invariant but shape dependent. So in fractal geometry, as far as my knowledge goes correctly, shape involvement has not been really addressed properly. Always we talk about grids, boxes, and these are all simple in a Cartesian coordinate system. They are like irregular grids and regular lattices. But in mathematical morphology, you have a lot of control, and you can introduce a kind of notation called structuring element. And as Gopal was telling, this is about data science here, and this name of the center will also change very soon. And in entire mathematical morphology, data will be investigated with another data. So if I say data is set X, and there is another data that is set B, and that B has certain characteristic information, it has shape, size, orientation, origin, and then symmetry. And it is a kind of query, and it can investigate any kind of set that is given, and then it unravels many hidden geometric, morphologic, and topological properties. And as many of us here are mostly with some geophysics, geomorphology, geoscience background, I say it is really worth, take it to heart and then spend a decade or so, and I am sure that you will get wonderful results, and then which you can really argue with lot of justification and logic. And as I mentioned, because they all knew each other, and Mandelbrot fractal geometry mainly relies on scaling, and then I think many of you are quite familiar with how he has written his first paper, How Long is the West Coast of Britain, and scale invariant properties and self similarities. And it is also called mathematically the Steenhuis paradox. And when you see the west coast of Britain, and then if you keep changing the step size from 1 meter to 1 centimeter, and you get different kinds of lengths. But by using the step size and the length as the function to the step size, and you can derive certain power laws. And those power laws are typically called as fractal dimensions. Or those power laws have scale invariant properties. Under all scales, it has the same power law, and we call that as a universal scaling constant. And there are many other fields like allometric analysis, allometry, why certain trees are growing much faster in the vertical direction than in its orthogonal direction. And so we have a completely different set of dimension analysis. It is not just standard dimension analysis, we have fractal dimension analysis. And so both will talk about complexity of the shapes, complexity of the functions, complexity of the processes, and but not many people have really tried showing some kind of links between fractal geometry and mathematical morphology. And as I mentioned, fractal geometry gives scale invariant properties, measures which are scale invariant, and the main component is the scale, but morphology talks a lot about not just the scale but also the shape. And what matters in geosciences or biological sciences is not just the scale but the shape. So that is where I have done some work. So these are the two founders, and Georges Matheron, and so incidentally they have, each one is having 2 PhDs. One was in mining engineering and another one was in pure mathematics. And the kind of mathematics they talk, and so it can really impress the theoretical mathematicians. The kind of mining engineering they speak, and so it all impresses many of us who has a lot of interest on geosciences and or biological sciences. And this entire mathematical morphology works on 2 fundamental properties, which we have to give the credit to the Minkowski operators and Minkowski subtraction, Minkowski expansion. There a set can be shrunk to the desired degree with another object, which I call it as a B, and then set can be expanded, and if there are no boundary conditions, that can be expanded until it occupies the whole universe. And for me it is the screen here. And these 2 operators are interestingly nonlinear operators, and in the sense when you perform shrinking followed by expansion, the set X won't come back to its original state. It loses certain information. That is a cascade operation called cascade of erosion followed by dilation. Actually, Minkowski subtraction is typically morphological erosion in morphological terms, and Minkowski addition is to add the 2 sets. The way we add the numbers, and we can add the sets and objects and functions, and then when you perform this erosion followed by dilations, these are 2 dual operations with the same B that you contract or erode the set X, with the same B when you try to reconstruct back by expanding it, it does not come back to its original state as long as X and B are non-homothetic to each other. So what is homotheity here? Similar in shape and similar in orientation. When X and B are similar in shape and similar in orientation, and contractions expansions will bring back your X perfectly 100%. But when they are non-homothetic, what are a simple example, a circle with a radius r and a circle with radius r minus 1, and these 2 are homothetic because these 2 are circles. And I also say when I draw a kind of circular object, and is it very complex, but because with our Euclidean geometry knowledge, and we will be tempted to say it is very regular shape because it is symmetric about the origin. But if I say no, you have no idea about Euclidean geometry, and Mandelbrot somewhere he writes that all Euclidean shapes are selfish shapes, and he argues that mountains are not cones, and clouds are not spheres, and dog's bark is not a straight line, but we try to approximate many things. But Mandelbrot looks at things at across magnifications. But to quantify that kind of features, and I have seen that erosion followed by dilations, when they are done with the B which is non-homothetic to the set X, and to put it in perspective, what is set X? And you have a elevation surface and you use a threshold value like 250 meters above should be zeros and 250 meters below should be ones. and that is my foreground. How does it look? And it may be very regular or very irregular. And so how do you characterize that? It has lot of geometric, morphologic and topological properties. To our naked eye, and we see, oh, this is the structure and we have a river network. And in morphological terms, a river network is typically the skeleton of the whole body. From the skeleton you can reconstruct your terrestrial surface. All that flexibility is there. And coming back, when I draw a circle, because of our Euclidean geometry knowledge, we say it is a circle, it is symmetric in nature, it has a smooth boundary. But if I put the B, which is completely non-homothetic to the circular shape that I have shown, and you have to explain it as a something which is very amorphous, irregular structure with respect to the B that I am choosing it. So it has a lot of both cognitive and computer vision involvement. And then, as I mentioned, two fundamental operations, erosion to shrink and dilation to expand. And then we have cascade operators, like are you performing erosion followed by dilation with the same B or a different kind of B, or with different sizes of B, and or are you performing dilation followed by erosion? And these cascade operations, and which I very vaguely mentioned, something builds and something destroys. What is that something builds? In terms of geomorphology, a tectonic activity is building something and weather related activities are destroying something. And these two are not happening in a linear fashion. If it is happening in linear fashion, and we should have seen our Earth's surface as a flat surface, but it is happening in a non-linear fashion. And that is where I used to see what is that is being built. Can we impose a dilation transformation? And what is that is getting destroyed? Can we impose erosion transformation? We try to apply in a simple toy models and how a terrestrial surface behaves under this kind of operations in a cascade form. Whether it is erosion followed by dilation, it leads the surface to lose its energy. And if it is dilation followed by an erosion, and the surface will gain the energy. And we are typically talking about two things here. One is foreground, another one is background, and we call it as a granulometric analysis and anti-granulometric analysis. As you keep on performing erosion followed by dilation, two consecutive erosions followed by two consecutive dilations, and n number of erosions followed by n number of dilations, and it surface is going to lose energy. And from that, what is the amount of energy that it is losing? And it is not uniform across the scales, across the cycles. And it is the loss of information will be rather heterogeneous. When it is uniform, when X and B are the homothetics. So mostly when we choose a family of structuring elements, and then we have a different kind of pattern in the loss of information. From there we compute the probabilities, and then subsequently compute entropy like index, which is also called uncertainty index, and which is also called a morphological entropy. And then it talks about the roughness calculation. What is the roughness? And we used to say roughness, there are many measures, many techniques, but in morphology I keep changing the B, the characteristics of B, and I compute a spectrum of roughness values. And so we take a global roughness values, it is not just sufficient. And how is it the roughness from left to right and top to bottom, diagonally, in all 360 degrees you can compute the roughness values, and you plot it as a spectrum. And of late I read a paper where it is mentioned after earthquake, aftershocks are large in number if the surface is very rugged, and if the surface is rather smooth and it has less number of aftershocks. And that is where I can bring some connection between morphology and then some kind of seismology. So we know Mandelbrot, and then so thanks to his son Laurent Mandelbrot, he shared this photograph when I had to put it in my Encyclopedia of Mathematical Geosciences, and he has shared this photograph. And then he talks about all scales, and as in morphology, and I was talking about shapes and functions and their complexities, and he also talks about a lot of complexities but across magnifications. And then it's all non-integer dimensions, because not like Euclidean dimension, you have dimension 1, 2, 3 and 4, time is the fourth dimension. And then we all know that when I draw a straight line, you know that it is a simple one dimensional feature, but when it is curvilinear and it is more than a line and less than a two dimensional space, and it should have some other dimension, not the integer dimension. So that limitation was there when we speak about just Euclidean geometry, and then fractal dimensions came into picture, and then west coast of Britain's dimension is not either 1 or 2, but it is 1.26, and he has given it with the different ways. One is analytical solution by following Koch curves, and both deterministic Koch curves and non-deterministic Koch curves, and then so Koch Triedek curves dimension, fractal dimension is 1.26, and incidentally west coast of Britain's coastline dimension is also 1.26. And we have many, and then universal scaling constant, power laws, allometry, Hacks and Hurst exponent, both were given by geoscientists. River Nile and how long is the longitudinal length and what is the transverse length. And had it been both lengths were of same length, and we should have seen a Hurst exponent of 1, and that is where we call the feature is self similar. Otherwise we call all other features which are not having the Hurst exponent of 1 are all considered as self affine. And then most of the features that we see in day to day life, right from botanical tree to cauliflower, and they have self affine features only. It is not like a well symmetrized feature. And then Hacks exponent is about length and area relationship. So length and area relationship, if it is standard dimension analysis, you should get √2, and that is 0.5, but we get much more than 0.5 for Hacks exponents, and these exponents were very well tested in all kinds of networks, right from river network to protein networks and bloodvein network and bronchial tree network, biological botanical trees, and everywhere these laws were nicely tested, but they were given actually by the civil engineers or geoscientists. So these are some connections, as I mentioned, morphology and fractal geometry. If you see them together, and it has number of applications in engineering, medicine, biology and social science fields. And then I believe I have to another 5 minutes, 10 minutes I will take, yeah. So this is we all know that it is a Koch quadric fractal, and why I have created this is the amount that I am projecting, the similar amount I want to remove from a simple square block, so that I will preserve the area, and then boundary I want to increase to infinite length. And if you look at Hortonian principles, the watershed, how they follow the networks and then contours inside, and if a watershed is following Hortonian principles, I want to create a watershed which simulate a watershed and which follows the Hortonian principles. And in all watershed studies, river network length increases with scale, but the area would be the same. And to simulate that, and we have taken this and a simple generating mechanism like this, and then something is projected, and so equal amount is being removed here, and the area is constant, but this is increasing. Its corresponding skeleton is this, and skeleton of any object is defined as a 1 pixel wide caricature which summarizes overall shape, size and orientation, and from the skeleton you can reconstruct your original object. And then what we have followed here, and so not fractals, but on a fractal object we followed mathematical morphology. Erosions, dilations and simple subtractions and logical operations has given me a skeletonization operation, a skeletal network of given any object, and it has number of applications in porous media studies. A porous media studies, given a rock porous medium, and you can actually decompose it into 3 topological quantities. One is body, one is throat and one is skeleton. So each of this is a subset of the bodies, and pore bodies, pore throats and pore networks, and then we can derive a host of power laws again, and all are coming under nonlinear physics. And then once I have this skeletal network, because it is a combination of skeletal subsets of several orders ranging from 0 to capital N, and from each order of the skeletal the subsets were dilated to the same number of order, and then assigned certain color code and then superimposed on one another. And then I could convert a simple black and white binary fractal object into a function which has topologically relevant regions within the thing. And so this is what I say, how to generate an artificial landscape. If I know a kind of B which can transform this into its skeleton, and what kind of B can really generate the internally topological prominent regions, and then I can create a kind of landscapes, and then I will show in the subsequent slides. And so morphology and fractal geometry have connections. One connection that I have shown is, so some transformations I am using from morphology on the fractal geometry, and but Matheron, Mandelbrot and Paul Levy, as I mentioned, these two are the some of the two best students out of 4 people whom he has produced. And fractals everywhere could be so to probably to characterize quantitatively. And there is another mathematician, and so Michael Bansley has written a wonderful book on fractals everywhere, and he started giving IFS, like iterated functional systems, and IFS code is so powerful, any object can be shown it as an IFS code, and then it has number of applications in signal transformations and image transmissions, and then so with convert into code and then transmit it, you tell the code and somebody can reconstruct it. All are very interesting then. So this is one just glimpse, and then so this is a synthetic landscape I have created, and then green and blue lines are typically the river networks and the reconstituted networks decomposed from this particular landscape function, and then hierarchical partitions of this landscape following some morphological principles. Typically all local minima will be taken as water bodies or depressed zones topographically, and allow those water bodies to flood with equal speed, and those flood front lines where exactly they meet each other, you draw a line which is a watershed line. So that is the principle used, and there is a watershed transformation here which was given by John Serra, mostly for image segmentations and data segmentations and all that. This is another study where this is an Apollonian space. Apollonian space has a fractal dimension of 1.36, and but what we have given here, Apollonian space can be decomposed into morphological shape decompositions with a regular octagons of various sizes. You pack that, and then you derive a simple relationship number wise size, and larger octagons are small in number and smaller octagons are large in number, and then that power law will give you again a scale invariant measure, and which is 1.36, close to 1.36. The moment you change from octagon to square, square to triangle, triangle to a circle, and then you keep getting scale invariant measures, but they are shape dependent. So that is what is a nicely captured idea, and which was well appreciated by, there was a mathematician in MIT and Peter Dodds, and who subsequently has become a social network related scientist. But he has made a question like a theoretical mathematicians or physicists would really appreciate deriving a scale invariant measure, but a core geomorphologist or geophysicist wants to see between the two basins what is that measure which can show the distinction to me. So that distinction will come from decompositions in morphologically with different shapes. We can create that B as per our will and wish, and you can change which can also be heavily used in visual cryptography. You want to transform my face and such that nobody can recognize, you just transmit it, and then you tell what B has been used to convert into a skeleton, and then only that person can really retrieve that, and it has many visual cryptographic applications. Okay. So this is how we have done for a realistic basin, and then this is for converting a fractal into skeleton. Then the internal topological regions simulate, and then you show them as a kind of vertical exaggerations, you have landscapes. But this raises a question, and how accurate is this landscape? And I used to say, you give me a proper boundary of your watershed and I will try constructing the internally topologically prominent regions within the basin. So that is one study. This is where I am talking about erosion followed by dilations, cascade operations of scale 1, 40, 80, and the different cycles I have done it, and it is losing its energy. In the sense, what is energy here? Sum of all elevation values is that energy. And then as I keep performing erosions followed by dilations with different cycles, and then it keeps losing its energy, and that loss of information is not uniform. And then that is where I compute the probabilities, and then I will follow simple Shannon's entropy equation to compute what is the roughness. So here it is the dual. Whole morphology works on dual operations. Erosion is dual to dilation, dilation is dual to erosion, and cascade operations are called, actually erosion followed by dilation is a kind of operation called opening, and dilation followed by erosion is called a closing, and then opening is dual to closing, and these are all nonlinear operators, unlike many of the operations there in wavelet theories. But that is where we see, should we really rely more on nonlinear theories or linear theories? That argument always goes on. And then from this I compute a granulometric index, from this I compute anti-granulometric index, and you have a terrestrial surface, and the region under each of the elevation values is a foreground, and the region, if you put a kind of hull around that terrestrial surface, whether it is a convex hull or a closed hull, and then whatever is there beyond foreground is called background. So is there a relationship between the foreground roughness and background roughness? I tried on a simulated structures, but I couldn't get any theoretical support. But this is where there are vulnerable regions which are very vulnerable for some various disasters, and we can really apply and see. But this is certainly a task for the young people, many of them are sitting here. So the following the same principle, we have lower Indus Basin converted into their watersheds. There are 31 watersheds, and we have computed roughness values for each of the watershed with a simple B, and with a B where the origin is at one of the vertices, and so in all 360 degrees we can change the origin, and then we keep getting B's of different types of things, and then we compute in which direction there is more roughness, in which direction there is low roughness. And so this lowest and highest directional roughness values were taken as the basis to classify the watersheds. And some of the things, and that probably I will skip, and so you have a very sparse contour data, converting that into dense contour data, we followed morphological interpolations. Again, it is very interesting that morphological interpolations are nonlinear, and because of that the nonlinearity property, and it is very interesting. These are just a binary things, and this is source data and the target data, and I want to create an interpolation function. Typically I compute the median function by using some morphological principles, and you have source and target, and you can generate one more interpolation. In a hierarchical way you can compute between median and the target, you can create one more. In a hierarchical manner between the source and target, when you have a very sparse data, you can keep generating many interpolation functions, interpolated functions, until there is no further scope for you to insert one more. Yes, this is how we will do it. Then other parts I just skip it, and this is just to give a kind of opinion piece. And digital elevation models, all these space agencies, they spend billions of dollars to generate DEMs, but not really utilized for scientific purposes. Those who are with some kind of mathematics background like discrete mathematics or morphology or fractal geometry, and the way they look at these DEMs are entirely different. These are exaggerated versions, and I have already shown, and then this is how I generate a landscape, and I quickly finish it. And but this one, let me just spend a minute. These are the three networks. All three are, any topologist is there, they say that topologically invariant. If someone knows about river morphometry, they will understand that these networks have same bifurcation ratio, mean length ratio and area ratios. And from there one can derive again fractal dimension, and log RB by log RL, log bifurcation ratio by log mean length ratio gives you the fractal dimension. But a geomorphologist does not want a similar measure for all these three networks, and they want what is that measure can really show the basic distinction among these three. What we have done, treating this as a skeleton, and you construct its body around it. Typically this is the skeleton, its body is this. What we have done, we kept on dilation followed by erosions for different cycles we have done, and we made it as a closed hull. And subtract the skeleton from this and you get a region like this. Instead of working on the network, you work on the hill slope regions, non-network space, and you pack that hill slope regions perhaps like this, and then you derive power loss. And that kind of power loss will show the basic distinction among these three networks, which are topologically invariant. And there are some set of equations, as I mentioned, that there is a pattern spectrum, loss of information, and then probability calculation and uncertainty index, and then at the end we get the roughness value or uncertainty index or morphological entropies with the different patterns, different shapes with rhombus, square and octagon. We get scale invariant measures, but they are all shape dependent. And so using those principles, and we have this global roughness based classification. This is high directional, high roughness value in which direction is there, and low directional roughness value. Based on those values we have classified them. This is again a lower end spacer. So this is just for visualization, a simple Koch quadric fractal that I have shown, and we could convert them into internally topological regions and show them with the different projections, and then treating that as a pore body, pore structure, porous media structure, you can convert them into bodies, throats and skeletons, and which you can see these are the bodies of different categories. These are the throats of different categories. These are the skeletons of different categories. And again, what are the ratios between order to order, and then we can compute some kind of complexity measures again. So taking the realistic rock, and then we have done the same process, and then we have classified them into bodies, and the bodies of different orders and throats of different orders and skeletons of different orders. Probably I will skip these things. These are for mostly spatial optimization for want of time, and let me just skip these things. So this is the simple morphological median between the successive contours, and between the successive contours we keep inserting one more contour by simply following, by taking intersections and unions, and then intersection of these outputs. This is dilated and this is eroded, and then intersection of that for all n values or lambda values above 0, and then you get one contour line in between the two successive contours. You keep doing it hierarchically, you can convert a sparser data into denser data. So you can perform again on this, and then you get still denser data. And so which was nicely published by my PhD student in IEEE TGRS. And that is a simple binary patterns, and these are the grayscale functions, a digital elevation model of at time t and time t plus 1, and I am calling it as fi and fj, and then we can hierarchically generate the median functions by simply following infima of both functions, suprema of both functions. Suprema will be eroded, infima will be dilated with respect to b with n values ranging between 0 to capital N. And then finally you take the suprema of all those outputs that you are getting here, and you get one median function here. If you have a very computationally intensive powerful computer, and all this can be done very nicely, very quickly, and so generate between, let us say there is a 6 months gap between the two desert dune DEMs, because dunes are very highly time varying, and you can see the patterns how it is changing, and whether it is really tallying with your realistic data. It's a wonderful physics of dunes, one can really handle it. So I will probably close here, and then a robust mathematical theory that science, engineering and social science communities need to pay attention. I would give more credit to mathematical morphology than fractal geometry, because it has complete mathematical basis, and which is also powerful AI tool. And Isabella Bloch is an engineer from I think University Paris 6, and she has written a wonderful tutorial how powerful is the mathematical morphology to say it is a AI tool. And I have several ideas, but we can discuss that later on. So these are some of the books that we have published, and these are just lectures. If somebody has interest to learn about very basics of morphology, and then how it is on NPTEL style we have presented here, about there are 18 lectures here. So thank you so much, and so it's a great honor, so particularly to talk about Professor Gaur's influence on my life. There is a 40 years, so I can narrate, but I don't want to tell it.
A most fascinating lecture I have heard.
Thank you, sir. Thank you, sir.
And
Yeah.
there were a lot of questions.
Yes, sir.
Starting with one which is that most self-organized structures which are far from equilibrium show fractal characteristics. Is it theoretically reducible? That's question number one. And the question number two was that apparently there is a zip law
Zipf law, yes.
which says that there is probably a fractal thing in time also.
Correct.
So can we sort of combine all these together to make a predictive model of how this landscape is going to evolve?
Actually, Zipf law was already reported as a kind of fractal power law, because Zipf has given the word lengths, and then he derived a power law. A smaller length words are large in number, and then longer length words are small in number. And Zipf, when he was in I think Harvard University, and his topic was something else, but he ended up giving this power law. So there are many such power laws, and which eventually Mandelbrot had to confirm that they are indeed fractals. But they were there much before fractal geometry, like Haughtonnian laws, bifurcation ratio and mean length ratio. The ratios are indeed the fractal dimensions. But neither Haughton nor Zipf must have mentioned that they are fractals, because fractals were not existing when they have given it. So that was one. The self-organized things, probably self-organized criticality that you are probably perhaps talking, like a dune formation, and after a certain as the dune is when you are pouring the sand, so it becomes like a kind of pile, sand pile, and then after certain number of times, discrete times, and it starts collapsing it. And that's what probably Deepak Dar mentioned about avalanches, and then avalanches follow again the power laws. But bringing that to a realistic thing like landslides, where exactly it happens, it's a challenge, but theoretically, yes. And then the self-organized criticality, I could hear both Deepak Dar and Per Bak. Professor Per Bak has written a book, Self-Organized Criticality, and how nature works. And then, but his lecture was heavily questioned by the audience, and why you are putting hand and then pouring the sand, and will it happen in the nature? So Per Bak was giving a talk in Singapore University where I worked, and yeah, self-organized criticality, but there are many systems, they self-organize, sir. Biological systems, there are many proofs, and but how a landscape evolves, I can simulate and show it, and by performing erosion followed by dilations, and with a host of different B's, and then there are different possibilities, it may go like this. But if I know how a landscape has evolved in the last million years back, how it was and how it is now, I can still try making a prediction by following some extrapolations. But I use the series of the sequence of those data sets, and then I can create a kind of a quench strip So, how a coastline changes. So, if it is in a synchronized fashion, it is changing and it is much easier to really predict what is going to happen, but it is not. And certain places there is erosion, certain places there is accretion, certain places there is no changes at all. And that is where you see the coastline changes are rather crisscrossed. And in last some 15 years if you take, and with an annual intervals, and but the coastlines when you draw, there are accretion zones, there are erosion zones, and there are zones where there is no changes at all. And that is where we require, one is a median function we compute, a median line, and then I have to create a pinch strip, and then I start multiplying with certain factor k, and then I say these are the possible extrapolated versions. I think somebody, a domain expert, has to confirm, yeah, this is a possible correct prediction that we may see, it may not be, and so probably I don't know whether I could answer. Thank you so much, sir.
Really fascinating.
Thank you so much, sir. Yeah.
No, other people must have a chance. No. You know, when you have a shape that is not completely regular, I can think of a fractal, completely regular shape like a Sierpinski's tetrahedron, but which is of course beautiful. But I suppose in every direction you will have the same dimensions in that. But in most other bodies, one would have fractal dimensions which will differ depending on the direction. I was wondering if there is, this could be a silly question, but could one work out some kind of eigenvectors?
Yes, yes, certainly, sir. Yeah, so with eigenvectors that can be, but here if I want to just stick to morphology or just stick to fractals, and what I was trying to desperately struggling was, so not all features are vulnerable to any kind of perturbation in all directions. Probably in certain directions these are very vulnerable. And perhaps a kind of asbestos roofing which is like this in a wavy form. And it is easy to break in this particular direction, but it is not easy to break in the other direction. I can give the spectrum of roughness values that I am talking, and in one specific direction the roughness will be very unique, in all other directions it will be in a different way. So in which direction it has a high roughness and is the direction in which the forces act, and it will get very vulnerable. But I don't know, but after spending almost 3 decades, I am getting these ideas, but I have no real energy to test those things, and that's where I really look for some young people that who can really take this subject. Not many have taken, sir. This 2 boys have taken, but they are theoretical mathematicians, and they only talk about theoretical mathematics, but it has numerous applications in both geo and biosciences, sir.
So, see, we have these networks, basically the observation networks we put in the Himalayan region and all. Can these be useful to design an optimum, make an optimum design where we should have these observation stations and other things?
Yes. So you can see that, and here I have not covered that slide. Here there are 66 water bodies. Sorry. Oh, God, sorry.
He will do. Yes.
There are 66 water bodies, and each water body has its influence zone. Each water body has its influence zone, and there are 66 influence zones here. If you have network stations, let us say 34 network stations, each station, if they are not with different signal strengths, and they will, what we do, and each using those points as the nodal points are the water bodies, and I will flood them. Flooding is nothing but I keep dilating all 34 simultaneously, and then where exactly those dilating front lines gradients are meeting each other, I draw a line, and that's how I generate influence zones here. And the core idea is here, why we have done this, 66 water bodies are there, all are going to be dried up because of some seasonal changes, and government has money to protect only one water body. So which is that water body to be protected, such that people from the other water bodies, they can come and fetch with minimal conflicts. So that was the idea, and we followed some dilation distances from every water body to every water body. We keep computing the dilation distances. There is a 66 by 66 matrix, and then from each water body, what is the maximum distance of the other water body, and all these maxima values, 66 maxima values you get, minimum of that maxima will get you the strategically located water body. This can be protected, and so its corresponding influence zone is this. And this is for computational geography challenge, we have done it, and then so we have just published it. Yes, it is possible. And so locating a new location to put a new thing, yeah, it is a nice spatial optimization problem. And you can use interpolations, or with distances we can always say that this is the potential location, will it really be conducive for your other conditions, and at least some suggestions we can give. Yes, yeah, that is possible.
Any other questions? Yeah.
Are there any applications in fluid flow problems of connection between morphology and fractal geometry? There is a lot of work on the fractal geometry in fluid flow problems, right? Okay, so even
Yes, sir.
chaos theory, for example,
Yes, sir.
right? So I have no idea what is the connection.
Fluid structures, and we can, if we have a static pictures, and the kind of those changes will be converted into either gradients or the skeletons. Actually, skeleton is a very unique gradient. So when you take an object, an irregular object, a typical gradient that we know, it is boundary, but the unique gradient is the gradient that can summarize overall structure and shape and size. So that is the skeleton. It has applications, but whether anybody has worked, I have no idea.
So you are saying one, the shape aspect is differentiating between, like the fractals is self-similar and everything looks same, right? Like, you showed three different
Networks.
Yeah,
True.
but the shape aspect differentiates between the three.
By changing the shape of the B, here B, as I mentioned, data is investigated with another data. That another data is B. The moment I keep tuning this B into different B, and the kind of measures that I get are scale invariant, but it is depending on that particular shape. With not all shapes, we will get the same scale invariant measures.
Because in chaos theory, what they do is, they compute the Poincare maps and their fractal geometry, the dimension.
Yeah.
But I think that is only one number. But I cannot distinguish between two different phenomena.
Correct.
If they have the same number.
Yes, right? I believe if we have a specific attractor out of chaos theory, and how simple is that attractor, and usually we compute Lyapunov exponent or fractal dimensions.
Right.
But morphologically, yes, we can give a host of different
measures.
Okay.
So you can actually distinguish between different attractors.
Attractors, yes. So whether it is really simple, if it is simple and I should get my uncertainty index close to 0, if it is complex, it has to go towards 1. And this is what I have written a very, it's a rather loose idea. How simple is the complex geological system, and how complex is the simple geological system, how simple is the complex geological system, and it is perception specific. And the moment that I say perception is my B, and if I use a circular structure with a circular B, and it is very simple, a circular structure with completely irregular B, and it is very complex. So what is that perception? Perception is the force that I am simulating it as a B, and there is processes involved here. I don't know whether I have answered your question to the extent.
Good morning, sir.
Yeah.
Actually, I worked in finite element where we have some irregular shape. Whenever I try to model, I make some element distortion.
Correct.
So you mentioned about shape. I always think about shape as the element. So what could be the difference whether your morphology can give me some answer to eliminate the mesh distortion?
Yeah, shape of the element, and so how big is that element, and what is its shape?
So I model maybe for one-dimensional two-noded or something like a curve 4 element or a 3D element. It can be like based on like whatever I have 1D or 2D or 3-dimensional shape.
Yeah, if it is a 3-dimensional shape, if it is like a kind of tetrahedron, and with tetrahedron its shape is very simple, there is no complexity. But if you use, let us say, some cuboids and you start inserting them, how many cuboids you can insert in the tetrahedron? And then until you minimize the unoccupied space in that particular tetrahedron, that gives you a measure. That gives you a measure. Actually, morphology has excellent applications in material science. And I have seen there was one material science professor, Salvatore Turcotte from Princeton University. He was the one speaking about pore bodies, pore networks, and pore throats. We have seen it with morphology. After publishing it, I think he was the one who reviewed it and he appreciated it. Similarly, the networks. With networks and the non-network space packing, sphere packing by unlimited packing growth by Peter Sheridan Dodds, and he has followed some classical mathematics, but we have shown with a discrete these morphological things, and they are there. And then if it requires some kind of discussion, perhaps if somebody like you, if there is someone, yeah, we can still see somewhere.
Mine probably
Yes,
is that when I am solving, let us say, some fluid flow problem, I make a grid, right? For example, say I take a rectangular grid, but then it depends on the certain regions where the flow is more complex. Right? So I think he's probably thinking, can I have more optimal shapes which will provide me a right solution in those regions? So is there some connection between what work you are doing?
It is, sir.
To finding right types of grids shapes.
Yes.
Probably that's what he means, I think.
Yes, I think it requires some hard thinking, and that it will, sir. Like so.
Otherwise, we simply use some very simple elements.
Elements, yes.
Like I said, in a grid, regular grid.
Regular grid.
Or I can probably have a curvilinear grid, but still topologically same.
Topologically same, correct.
But he is looking at now bringing the shape into the picture, which makes it more optimal.
More optimal, yeah.
Optically more efficient also.
Correct. No, for me, the more optimal feature that I can inscribe into another shape is that shape itself. That's what I am saying, homothetic, similar in shape and similar in orientation. And packing a box with a cube is perfect, and so such that there will be no void at all. But packing a box with some kind of, let us say again, tetrahedron or octahedron or octahedrons or hexahedrons, it will leave at the end of the packing, and then there will be some dust-like information which cannot be packed.
How do you fill those gaps if there are other solutions? Because that is important in, let's say, solving some numerically. Those are important gaps.
Those are important gaps, but that would be just dust, and because they are so small and you cannot inscribe anything into that.
So it would be okay to do that? I mean, to solve a problem where I can ignore them?
Yeah, so I think we have ignored, and then we have ignored, but our focus was just to derive a power law.
That's okay.
Yeah.
We're trying to understand the utility of this one to
Yes.
generate, let's say, shapes.
Yes, sir.
Which will be used for solving, let's say, some set of differential equations.
Yeah.
Subject to conservative laws.
Yes.
So these little gaps they were talking about. It arises in our practical problems when we solve the fluid flow problem.
for fluid flow problems. But
So, because it is like a gap you're talking about. But that is the error that is leading to
shown
the
there, yeah.
But if you can show that that error can be minimized by finding more optimal shapes,
Yes.
that would be a practical application of that.
But that is actually a challenge, sir. There is a subfield of mathematical morphology is adaptive mathematical morphology. And if I give a data and I will ask the person, and which B I can use it to process this to get what? So, what is that most adaptable B that I can derive from here? So, as Professor Gaur was also asking, something is changing with time, and what should have been the B when it is getting transformed into some Fi to Fj, and if we can really derive that, is that B throughout acting on it? I do not think so, but this B also evolves. I think it is like a kind of coupled thing, and then you have to first predict how time dependent problem. Yes, yeah.
I have one question.
Yeah,
I was just wondering,
yeah.
in order to create a shape, you need energy.
Yes, sir.
I mean, all these fractals, there is information or energy, I might say. So, would it be a pertinent question to ask that within a given circumstance, what is the structure I can sustain with this energy?
So, if you have a specific structure and one is that to make sure that structure does not lose its energy, there should not be any process happening, one possibility.
No, but in a conservative system, I don't want to lose it.
Ah.
It will change shapes
It changes shapes, yes,
as time evolves.
as time evolves. And so, can we find out the pattern in that change of shapes?
I think something like that is what.
That is at least one is to create so many interpolations between that evolving shapes, such that this discretely evolving shapes will be made to close to continuum, and then we can make predictions, and then yeah, I think that
That's our main problem in many
predictive system, yeah. I do not know whether there is any study on the morphological dynamics of simple shapes. Simple shapes are like probably like sand grains, how grain growth mechanism works, and some probably material scientists and the centering processes they apply, and then how fractal islands will form as heating cooling happens.
Depending on whether you use sand grains or rice grains for fun.
I do not know.
Sand pile experiment.
Yeah, so with the wet rice and dry rice, this feeder and feeder, father and son, they have done several experiments, and there were published studies, but it is purely on fractals. But their shape of the grain matters, and the avalanche structures and avalanche sizes will keep changing if it is completely dry and it has a different kind of avalanche patterns, and if it is wet rice and then it has a different avalanche patterns.
Yeah, I have one.
Yeah, you are asking.
In your talk, you have mentioned that superiority of fractals over wavelets.
No, I don't say superiority, and the people will question me.
No.
And morphology.
Morphology.
Morphology, I felt that it has a good mathematical basis. And in fractal geometry, of course, Mandelbrot is a thorough mathematical physicist, but one book I have seen with good mathematical basis is Mathematical Foundations of Fractals by K.J. Falconer from Warwick University. But why I say it talks only about scale. As I mentioned in the scale, the way I look at is not in a gridded form. The way I look at is with a circular form or triangular form, it all changes. And the perception with which you are looking at is not quite seen in fractals, but I am not a critic of fractals, because scale invariance is so important, as the physics, laws of physics and these power laws have mentioned so many interesting things. Warm-blooded animals, and then cold-blooded animals, and then animal sizes and numbers, and animal, so all these are very nicely derived. The whole allometric scaling, fractal scaling, you know, the Barabasi, Rekha Albert, and they have done a lot of work on these power law relationships, and mostly physicists from, I think, either Harvard or Santa Fe Network labs. Yeah, so, but your question, and yeah.
I just thought of how is your comparison between fractal transforms and wavelet transforms?
No, wavelet transforms are all linear, right? But morphology transformations are all non-linear. But was there a study that linking these two things anybody has done? But I know one, but he didn't survive long. Hank Huysmans, and he was the one trying to give morphological wavelets, and to show the connections between wavelets and mathematical morphology, because it is, one is completely linear transformation, another one is non-linear. But unfortunately, Hank Huysmans didn't survive, and he had a hemorrhage, and then he died, brain dead. I think beyond that I didn't see any studies, but I think if someone has brings some connections, but there are some nice technical reports of Hank Huysmans. Theoretical grayscale morphology he has published in some IEEE transactions, and he was from CWA Amsterdam, Netherlands. Yeah.
Let's thank Professor Dayasagar for wonderful lecture.
Thank you so much.
Followed by a very nice discussion. Thanks.
Yeah. No. When I reached here, half an hour, 1 hour before I reached, and someone mentioned, Imtiaz has mentioned Professor Gauri is coming. My tension has increased.
You know, I'm already drafting an email to you asking for some references.
Sure, sir. Yeah.
This is really fascinating.
Thank you.
I can see the many applications of this idea.
Yes, sir.
Thank you, sir, for that intellectually stimulating and enlightening session. I'm sure everyone here has gained new perspectives on mathematical morphology, spatial optimization, and fractal geometry. Now we have the release of our in-house Hindi magazine, Pratiman. I request our Hindi officer to kindly come forward.
नमस्कार। आज राष्ट्रीय विज्ञान दिवस के इस शुभ अवसर पर CSIR 4PI की हिंदी गृह पत्रिका प्रतिमान के प्रवेशांक का विमोचन किया जा रहा है। इसमें वैज्ञानिक लेख हैं, सामान्य लेख हैं, उपलब्धियां हैं, कार्यालय की गतिविधियां हैं, कविताएं हैं, कहानियां हैं और आदि लेखों से पिरोया गया है इस पत्रिका को। और मैं अनुरोध करती हूँ, और ये एक परंपरा की शुरुआत है जहाँ विज्ञान अर्थात विशेष ज्ञान और भाषा के समन्वय से उल्लेखनीय उपलब्धियाँ प्राप्त की जा सकती हैं, और ये एक राजभाषा नीति का एक अनिवार्यता भी है। और मैं अनुरोध करती हूँ हमारे निदेशक महोदय से और आज के हमारे मुख्य अतिथि और इम्तियाज़ सर से कि वे पत्रिका का विमोचन करें। बहुत बहुत धन्यवाद।
Thank you, ma'am. It is my now privilege to invite our director to deliver his presidential address.
Good afternoon. Just wanted to ensure what is the time, and happy Holi to all of you. I think this is a great occasion, and my major motive to bring him here, I have been thinking about bringing him here for quite long, was to see that we have actually lost touch with basic sciences. That's something we have been carried away by the requirement of engineering aspects, technology aspects, but the basic science which builds the future engineering is something that was almost kind of missing. And then that's the reason why specifically I wanted Professor Gaur, Dr. Bhogle, Dr. Mutkavi and Dr. Dutt to be here, because I'm sure many of us haven't heard such talks for quite long. So that's very important that we listen to such talks. Sir, thank you very much for giving such a wonderful talk. And it also, after that, it almost looked like a brainstorming session, not as a question answer session. I think we should have a brainstorming session at some time to discuss more on, because this is not a particular science. It's a tool kind of thing which multiple problems can be solved using this tool. And of course, I have heard him earlier also in one or two occasions about his work, especially in geosciences, the work that he has done in these fields. Also, I think a wonderful talk by Dr. Usha, talking about two important women scientists who have actually had changed the atmospheric science field in the country. It was wonderful to listen to you as well. And his talk was basically talking about the two fundamental science problems of morphology and fractals. I don't know, Mithun, I think, left from here. He was there. He has been working on this spatio-geometric foundational model. So I think this morphology gives you the shape, and geometry is given by these fractals. I think that's a wonderful combination which we should be integrating into the foundational model that we are developing as part of the CLAIM project. I think there are lots of AI applications which also can take benefit of these methods, other things. So that's something which we should actually look at. Regarding the Science Day that we are celebrating, I was just trying to look at, I think everybody knows why we are celebrating Science Day on February 28th, though February 28th this year was a Saturday, so we are doing it today. But looks like February 20th is a very lucky day for science. It's not only a Science Day, it's a lucky day for science. So I thought I'll gather some more information about what all happened, what all scientific innovations happened on the particular day. So that's something which I thought I should talk about. Obviously, we know 1928, C.V. Raman, the Raman effect, which he discovered, basically which talks about light carrying molecular signature of substances. That's typically the work that he had done, for which he got 1930 Nobel Prize. But in 1953, on the same day, February 28th, James Watson and Crick, they actually talked about the double helix structure of DNA, which another path-breaking discovery that they did, which later had transformed the way we talk about medicine, biology, then genetics, all those things. It's already 70 years after that innovation or discovery what has happened. We still talk about that. It's so useful, and it has exactly happened on February 28th. So that's kind of a coincidence. Then if we talk about more coincidences on February 28th, in 1935, Robert Bartson and Watt, they designed radar. And that is another transforming technology that transformed the way we talk about weather studies, we talk about air traffic control, all those
till now we are still talking about the radar and all. So that's one more invention which happened on February 28th. So it's a very lucky day as such for the whole world as a science thing. Though we give importance to the Indian context, but then there is a lot of things happened on that day. In fact, it was so much that US National Science Foundation was also founded on February 28th, which I think people feel so proud, like lucky if they get a NSF funding for doing a project. Such tough it is to get a fund, but that is again, it may be a coincidence, but it was again on February 28th, which was on which it happened. And in 2007, NASA's New Horizons spacecraft, which was going to Pluto, that historic Pluto travel, crossed Jupiter, and they tested for the first time how to use the gravity to increase the speed of the spacecraft. So I think it's there is some word that is slingshot. So how to control when they cross the Jupiter or any other this one. They can control using the gravity field of that particular planet. They can actually change, either they can increase the speed, they can decrease the speed also. Even when they cross moon also they can do that. So first time in 2007 on particular date of February 20th this was done. And very close to India, ISRO in 2021 PSLV C51 mission. They actually sent Brazil satellite along with many co-passengers, highlighting India's growing strength in the space. So there are so many coincidences on February 28th, including at least 10 Nobel laureates are born on February 28th. So that's the kind of lucky science day for this February 20th has been. I thought with some in fact I was going through one article by Professor Kishore Paknikar. He right now the INRF professor at somewhere in some institute in Pune. He had this article where he had brought out all these coincidences that which happened on February 28th. So just to say that we don't celebrate Science Day just for the sake of Science Day. I think this should give us inspiration to work for looking at science. Maybe, of course, there is lots of pressure on us to deliver some product, some this one, but for a long-term benefit, for future technology to develop, we also need to spend some time, or maybe some people should spend some time on basic science research. That they need to be given special thing other than publications. They cannot come out with products and other things, but then some special setup has to be created for such people. So I think that should be an inspiration. From his talk you would have understood like how deep he is into the subject, and he has spent 30 years to understand. And then he also said, I think another 10 years, if somebody wants to do research, another 10 years work is still pending to do in those fields. So thank you very much, and wish all of you again a great National Science Day. Thank you.
Thank you, sir, for your visionary words and continued encouragement towards scientific excellence at CSIR 4PI. Gratitude is the fairest flower that blooms from the soul. I invite Dr. Sendil Kumar V, Senior Principal Scientist, to propose the vote of thanks.
Distinguished dignitaries present on and off the dais, esteemed colleagues, project staff and students, good afternoon. On behalf of the Institute, it is my honor to propose the vote of thanks. First, I would like to express my sincere gratitude to our chief guest, Professor B.S. Dayasagar, Head ISI, for delivering the National Day lecture, particularly about mathematical morphology, shapes. Thank you, sir. But particularly like you had a lengthy question and answer, we are happy. So also I would like to thank our chief guest for releasing our institute's Hindi magazine. Now I request our director CSIR 4Pi to honor our chief guest by presenting a memento. I also extend my heartfelt appreciation to our director, Dr. Gopal Krishna Patra, for his unwavering support and encouragement and his presidential address. Additionally, I extend my gratitude to Professor Vinod Kumar Gaur, Honorary Scientist and former Secretary, MOES, Dr. Vidyadhar Y. Mutkavi, Honorary Scientist and former Head CSIR 4Pi, Dr. Srinivas Bogale, Honorary Scientist, and Dr. HNV Dutt for their kind presence. I thank Dr. Usha Haisyagar for presenting Woman Scientist Talk. Further, I thank her for mentioning about Anna Mani's inspirational work and Dr. Sulochana Gadagil's work. In this list, I would like to add about Dr. Marie Curie, the woman who struggled because in Poland around 1890s, higher education was not at all possible. So she migrated to France, she struggled, she won the Nobel Prize in Chemistry, and her husband died. Later again she bounced back, again she got the Nobel Prize in Physics. She is the one and only person, maybe male or female, got 2 Nobel Prize in a 2 distinct field. So she may be like one of the inspiration. My sincere thanks goes to all the HODs for their cooperation, including TMD, IDRD, BRSD, admin, finance, stores, office of the director, FMS, NAL security, canteen, and many more. I would also like to acknowledge the invaluable efforts from my colleagues, project staff, support staff, students, and the entire 4Pi team. Finally, I thank every one of you, as well as those who have contributed directly as well as indirectly to this particular event's success. Now, I request everyone to stand for the national anthem. The program is concluded. Thank you.